Okay, this is a video to outline uncertainty in graphs and linearizing curves. First, here's just some details about good formatting of graphs. Some of this will be taken care of for you if you plot your graph on a computer, like clear scale markings and clear and small dots. But just remember that you should have a clear and unique title that doesn't just repeat the things that are on the axes, and make sure that you label your axes with words and units. By the way, the IB uses a slash like this to indicate that the unit is coming afterwards. Let's talk about uncertainties in graphs. So uncertainties are shown graphically by drawing error bars. So error bars might look something like that in the vertical dimension and like that in the horizontal dimension. And they could be different for every different point. Now, think of the error bars as creating a kind of box. This one I haven't drawn very well. So a kind of box like that, and your line now should go straight through each of those boxes. So imagine that my line of best fit was something like that. Okay, hard to draw straight on this, but there we go, that's my attempt. Now, by the way, notice that note that the IB refers to curves as lines too. So if the error bars kind of trail off like in this direction, the points trail off in that direction, your line could go like that as well. If they ask you for a line of best fit, it doesn't imply that it's a straight line. So there's our line of best fit, but we also can have maximum and minimum lines. So if I start from here and go to here and go through all the error bars, I could create that's not very straight, I could create a line that goes a bit like that, and this is my maximum slope line. And I could also create one that is a bit like that, or in fact even more so, like that. Let's say, imagine I hit there, and that's my minimum slope line. Now, I've got a maximum slope, a minimum slope, and a best fit line. And I can use my maximum and my minimum slope line in order to get the uncertainty in both the slope and the y-intercept. The y-intercept could be here, and it could also be all the way down here, but this is my best estimate of the y-intercept. So for both the slope and the y-intercept, you can use half the max minus the min to find the uncertainty. By the way, when you give an equation for the graph, it should use the variables on the axes. So let's say this is speed in meters per second, and this is time in seconds. Then your slope is going to have units of the y-axis over the x-axis, so meters per second squared. And our equation, let's say the slope ended up being 10, might be v is equal to 10 meters per second squared times t. Again, we're not using y here and x, we're using the variables that are actually on our axes. And we'd be finding the slope as part of our experiment. Okay, carrying on, that's an example of a linear graph, and we're going to use that here to explore a little bit further. So let's say that we actually did an experiment, and we started from time of 0, and we had a speed of 0, and then after 1, 2, 3, and 4 seconds, we had speeds of 10, 20, 30, and 40 meters per second. So we could create our graph, and we would get this equation from it. Now this is of the form y is equal to mx plus b. Now b here is 0, but our variable on our y-axis is y. In this case, it's speed. Our variable on the x-axis is time. And our slope is the acceleration. That's why I wrote 10 meters per second squared above. In this case, the y-intercept is nothing. Now, if the graph ended up looking like this, that would be an indication that there was some systematic error, because our non-zero y-intercept indicates that all of our values are skewed in the same direction. We've got an okay slope. In fact, imagine all the points were like this with very small error bars. We've got an okay slope, but our y-intercept is off. The whole graph is shifted up. That's an indication of systematic error. Now, other graphs will yield points that are not straight lines, and you shouldn't try to force them to be straight lines if that doesn't work. Rather, conclude that the data is not linear, and then try and linearize the data. So here's an experiment where we take a cart sliding down a frictionless inclined track, and we get this nice parabolic curve. We've graphed displacement versus time. Now, we could now try and linearize that by hypothesizing what the relationship is there. We saw a parabola, so we're going to try a a quadratic relation, graphing displacement versus time squared. What we've done, if you look back here, is we've taken all the times, 1, 2, 3, 4, etc., and we've squared them, 1, 4, 9, 16, etc. The distance is exactly the same as we had before. Okay, so now we're going to graph the same values on the y-axis, but different values on the x-axis. And because they're different values, they have different units. The units are squared as well. And now we see we get a really nice straight line. So this is called linearizing the data. When you change one or both of the variables, manipulate them algebraically in order to get a straight line. Again, it's a straight line, so it's the form y is equal to mx plus b. Y is our distance. B is again 0. T squared now is our x value, right? That's the value here on the x-axis. And that means that our slope is going to be equal to half the acceleration in our example. So there's an example of linearizing graphs. Just make sure that you're careful when you're doing this, which symbols are representing variables and which ones are representing constants, because that can get you tripped up. Your page has a bunch of practice, and the answers are at the very end. Carrying on, let's talk about a more complicated example of linearizing. When you know that two variables are related through a power law like this, where a and b are constants, we could just graph y versus x to the power of b. So that's just another form of doing what we were doing before, or another way of stating that. Right here, we know that this is a constant. But sometimes we don't know what that exponent is, so we can't take that approach. And instead of just guessing, something that we can do is employ logarithms. So logarithms are handy because they allow us to bring that exponent down. For example, let's say you have this kind of equation, and you don't know what these two constants are. So this is different from the example above, where we knew what that was, or we could guess that that was a 2. Here we don't have a good idea. So instead we can use logarithms, and the properties of logarithms let us bring that exponent down. Following along here, taking the logs of both sides, we can separate out at this point because of the rules of logarithms into log k plus log r, and then now we can kick that n down. That's another rule of logarithms that if you haven't learned already in your math class, you probably will be learning soon. We could be using any other kind of base. We could use natural logarithms as well. Same kind of thing, allows us to split it here into a sum and then kick down the exponent. So now we're going to graph. This is our y value. This here is our x value. That makes this our slope. And this is our y-intercept. So we're going to graph log f versus log r, and that's going to give us a straight line with slope of n, that's our exponent, and y-intercept of log k. Okay, so if we graph log f versus log r, let's say we get a straight line graph now, or we will get a straight line graph now. The y-intercept is going to be log k, and our slope is our mystery exponent. Now, if we want to find what k is, remember from rules of logarithms, log k is equal to, let's just call it our y-intercept now. Rearranging into an exponential statement, that means that 10 to the power of the y-intercept is equal to k. So to find k, we do 10 to the power of the y-intercept. So this is a process for finding those constants when we really have no idea how to start. We can use the same process with natural logarithms or any other base, and this would have worked with the process or with the equations above, v is equal to, or excuse me, s is equal to at squared. When we knew the exponent, it's just really not necessary. Okay, so that's a quick introduction to linearizing graphs and uncertainty in graphs.